Have you ever wondered how databases actually talk to each other? You know, how they can dig through these just unimaginable mountains of information to find that one thing you're looking for? Well, it turns out they have a secret language, a core logic called relational algebra. And today, we're going to learn how to speak it. I mean, really think about it for a second. Every time you search for a product or a song or look up a friend's profile, there's a massive database in the background doing some serious detective work. And it's not magic, not at all. It's a very precise set of operations. So, how does it crack the case?
All right, here's our game plan. We'll start with the case of the data, just to get a feel for our evidence. Then we'll get into our three main techniques: the magnifying glass, combining clues, and connecting evidence. After that, we'll put it all together to crack the case, and we'll finish up with a look at our complete detective's toolkit.
Okay, first things first. Before you can solve any mystery, you have to understand the evidence, right? You got to know how it's all organized. And in the world of databases, that means we need to understand tables. Now, the fancy official term for a table is a relation. It's just a collection of rows, which are sometimes called tuples, and columns, which are called attributes. But here's the key rule, the really important part. Every single row has to be unique. That's because a relation is basically a mathematical set, and in a set, you just can't have duplicates. Every piece of evidence is one of a kind.
So for our little investigation today, we're going to be working with these two evidence files. First up is this movies table, and we also have a directors table. Now take a look at that director ID column in the movies table. That shared piece of info, that's the golden key. That's the clue that's going to let us connect everything together later on.
Okay, we've got our evidence laid out. Now it's time to pull out our very first tool, the magnifying glass. This technique is all about filtering out all the noise so we can focus on the specific clues we actually need.
So let's start with a really simple question. We have this big list of all the movies, but let's say we only care about the science fiction ones. How do we pull just those records out of our table?
For a job like this, we use what's called the select operation. You'll see it represented by the Greek letter sigma, and you can think of it as literally a powerful magnifying glass. You just give it a condition, something like the genre has to be sci-fi, and it goes through every single row, keeping only the ones that match.
And boom, here's what happens. We apply that select operation to our original table with our genre equals sci-fi condition, and we're left with this much smaller, much more focused table. See? Only the sci-fi movies are left. We've just isolated our first set of clues. Easy, right?
But what if we don't need all the information about those movies? That's where our next tool comes in handy. It's called the project operation, and it's represented by the Greek letter pi. Now, this isn't about filtering rows, it's about choosing which columns you want to see. Think of it like a spotlight, letting you focus only on the attributes you care about, like maybe just the title and the year.
Let's see it in action. We take our full table, we apply a project for just the title and year columns, and we get this nice, clean two-column list. We've used our spotlight to just slice away all the details we don't need. So here's the key takeaway. Select picks the rows, and project picks the columns. Okay, awesome. We know how to narrow down a single file of evidence. But, real detective work is hardly ever that simple. It almost always involves comparing and combining different lists of clues. For this kind of work, relational algebra just borrows the classic set operations you might remember from math class. A union could merge, say, a list of old movies with a list of new movies. A difference could show us directors who made sci-fi movies but not thrillers. And an intersection, that would find movies that are on both lists. These are just fundamental tools for comparing what you've found. And now it's time for the most powerful technique in our entire toolkit. Seriously, this is where we go from looking at isolated facts to seeing the entire picture. This is how we connect clues from totally separate files. So one way you could try to connect our movies and directors tables is with something called the Cartesian product. This is, it's the brute force method. It takes every single movie and just blindly pairs it with every single director, creating every possible combination you can imagine. It's like casting the widest, dumbest net possible. And yeah, here's what you get. It's a huge, messy table that is filled almost entirely with nonsense. I mean, sure, you get a movie correctly paired with its director somewhere in there, but you also get it paired with every single other director. So the main takeaway here is that this creates a ton of noise, and it is not very helpful.
So we have a choice. We can use the Cartesian product on the left, which just mashes everything together and creates a lot of noise. Or we can use a much, much smarter way, the natural join. It doesn't just combine things, it intelligently connects the dots to create actual meaning.
And this is it, the natural join. It's the smart connection. It works by looking for columns that have the same name in both tables. In our case, that's director ID. And it only combines the rows where the values in that column are a perfect match. This is really the detective's secret weapon for making logical, meaningful connections. And just look at that beautiful result, a single, clean table where every movie is perfectly linked to its director, along with all their info, like nationality. There's no noise, no nonsense pairings. We've just successfully connected two separate evidence files into one single, coherent story. This right here is the absolute heart of how relational databases work. All right, we have all of our techniques. We can filter, we can focus, and most importantly, we can connect. So now let's put it all together to finally crack this case and get a conclusive answer. To get to that final summary, that bottom line, we use what are called aggregate operators. These are little functions that take a whole column of values and just boil them down into a single result. We can get the sum or the average of a column, find the max or the min value, or, as we're about to see, just count the number of items. So let's ask a pretty complex question. How many sci-fi movies in our database were made by directors who are not from the USA? Well, by combining a join and a select and finally a count, the database can do all of that work in a flash and give us back a single, powerful answer: 3. This is the payoff for learning the language. So let's do a quick recap of our Complete Detectives toolkit. Step 1. We use the Select magnifying glass to find the right rows. Step 2, we use the Project Spotlight to focus on just the columns we need. Step 3, we connect different tables with a smart join. And finally, Step 4, we summarize our findings with an aggregate function to get that one final answer. And that's really it. This simple set of tools, Select, Project, Join, and the aggregates, they form the logical foundation for how we interact with pretty much all of the world's data. It's the powerful, underlying language that turns all that raw information into clear, simple answers. So, now that you know the basics, the real question is, what mysteries would you want to solve?